If it says that the cylinders are rigidly connected, it means that as one of the axles or discs rotates, the other will rotate as well. So if you at some point find alpha or omega for either of these disks, it's the same for both disks, okay? They're rotating at the same angular velocity or with the same angular acceleration as well. So they're moving in tandem. Let's see, so they can spin freely on the common axle, frictionless axle, which is pretty much always going to be the situation. We haven't had a situation like that where we're going to have friction on the axle itself. The moment of inertia of the pair of cylinders is given. So you don't actually need to determine I, and you don't have to worry about, okay, I is, what is this, a disk? 1/2 mr squared, but there's 2 disks, so how do I do it? No, they're giving you the total I value for the entire system. So there's no need to look at a table to look up these values here. You're also given the radius of the first disk and the radius of the second disk. You need those because those are going to give torque due to the ropes hanging, right? Because the rope has tension, so there will be torque acting on the system at those 2 different radii lengths. And you're also given the mass of the first hanging block. The second you are not. So part A asks us, determine the mass 2 such that the system will remain in equilibrium. So when the system is in equilibrium, we have to think about the simple fact that the net torque equals 0. So let's start this first problem here, this first part here, and I'm going to put it below. So I would start by saying first, the sum of the torques equals I alpha, but in this case, we know that the sum of the torques is equal to 0 because it's not rotating. Determine M2 such that the system will remain in equilibrium. All right. So if that's the case, we have to look at this and say what torques are acting, right? We've got the torque from the mass on the right, M2, and the torque from the mass on the left, M1. The mass on the left is going to cause a counterclockwise torque, so that's going to be a positive tau 1. And the mass on the right is going to cause a negative torque, so that's going to be a minus tau 2, and that equals 0. Then we know that the formula for torque is force times distance times the sine of theta, but almost all of these problems, theta will be 90, as most of you noted in the quiz right away. So it's really just F times R, where F is the tension in the actual cable. Okay, so we have to think about this problem and say to ourselves, all right, well, what's physically going on here? So the tension in the cable, how are we going to figure out the tension in the cable for a problem like this? What are we going to think about? What's the tension in each cable if it's in equilibrium? Feel free to just unmute yourself and respond. Good. So on the right cable, it's M2 times gravity. On the left cable, it's M1 times gravity. And again, that comes from the fact that if we look at a free body diagram right now, in a state of equilibrium, for mass 1 and mass 2, this will be tension 1 due to M1G. This will be tension 2 due to M2G. Okay, and then obviously the pulleys up here, or the discs rather, are up there. So we've got force times R, so this is going to be the tension in cable 1 times R1 minus the tension in cable 2 times R2. And what we'll note here is that, again, the tension is equal to, as Chris said, the mass times gravity, or the downward force. So on the left side, we're going to have M1G times R1, and this is going to be M2G times R2. G is common, so G drops out. And then as a result, what can we do? We can solve this equation for M2. So let's move M2R2 over to the right and then divide by R2. So moving M2R2 to the right and dividing by R2, we get M1R2, M1R1 I should say, right? This should be a subscript level 1 here. Put the eraser tool here, there we go. All over R2, and that'll give us M2. R1 over R2 as a ratio is 0.5 over 1.5, which will be 1/3. And then 1/3 of 20 is just 20/3. Okay. So part A is a system that is in a state of equilibrium. Now, we in class haven't even really talked about rotational equilibrium, right? We've alluded to it, the idea that if something isn't rotating, we would say that the net torque is 0 because then there's no alpha value. If it's not rotating, alpha's got to be 0. So what we'll notice here again is that equilibrium indicates that we have no net torque, and the net force on the system is also 0. Okay, the net force. And we'll see that more in a chapter 11 example that we're going to do probably early next week, actually. Okay, any questions on part A right there? All right, so let's take a look at the next 3 parts. So in the next 3 parts, it says the following. Mass M2 is now removed and the system is released from rest. So now this becomes the same as the quiz problem when you think about it. Without M2, it was exactly what the quiz had. The quiz was an object hanging from a rope, and that was then released at time equals 0, and it was able to fall. Keep in mind, it never said it was cut, like the cable's not cut. So when they say released, it's as if somebody's supporting the mass that's acting on the pulley, and then it's let go. That support is gone, and now the mass pulls down, causing the wheel to rotate one way or the other. So for part B, M2 is now removed. That's fine, so we can drop that from our diagram. So now all we have is M1 acting. And M1 is acting at a distance R1. So visually we can see that if we just go up to the diagram and think about, okay, this is now gone, right? That's not there anymore. But the overall I value is still the same. We don't drop off the second big disk because suddenly the second mass is not there. The overall I value is still 45 kilogram meters squared, which we did not use in part A, right? Because in part A we had no alpha, so 0 times I is still going to be a 0 there. Again, because this, remember, this was 0 in the first part, that little alpha. Okay, that alpha was 0 there. So for part B, let's take a look. It says determine the angular acceleration of the cylinders. Determine the angular acceleration. So part B is asking us to find alpha, okay, which is different from the quiz today. Again, the quiz today, you were trying to find the acceleration of the hanging mass, which you could find by the relationship that we know, and I'll put them up here. Remember these relationships for this chapter. We know that A is equal to alpha r, V is equal to omega r, and S, right, the arc length, or D in this case, or X, whatever we want to call it, is equal to theta r. Those are the 3 relationships we know for a system like this where there's no slipping occurring. You're hysterical on now. So we're trying to figure out in this problem what alpha is for part B, the angular acceleration. So the key is to recognize that we do not have a system that's currently in equilibrium anymore. If equilibrium still existed, then alpha would be 0. So we must have some sort of system that is rotating at some rate. So for the second part, we want to look at the net torque again and say that again, the net torque equals I alpha. Now the only torque that's acting comes from the first mass. So that first mass is going to be tau 1, and that again equals I alpha. And tau 1 is tension in the first cable times R1, which again equals I alpha here. Now, what is the tension in that cable? Well, we have to think about this problem and ask ourselves what's happening here. So the tension in this cable, let's think about this. Let me think for a sec. I want to approach this. Let's look at the equation. Let's see. In the vertical direction, I'm going to look at the equation for this right here now. When this is released from rest, we can say now that tau 1 minus m1g is going to equal m1 times its acceleration downward. Again, what am I getting this from? I'm getting the sum of the forces in the y direction equals 0. Where'd Spencer go? Okay, there he goes. He's coming back. So in the y direction, we've got this equation here, and we know that our A value, right? Our A value is really alpha times r. That's what the A value is there. So what can we do? We can write T1 minus M1G equals M1. Now here's the thing. In this problem, it's important to note A for this mass is going to be a negative quantity, right? The linear, the linear acceleration going down, that's going to be a negative value. The alpha value in this problem, what kind of a sign is that going to have? If the mass is hanging on the left side, right? The mass is hanging on the left side, so it's going to rotate in a counterclockwise direction, right? It's going to rotate like that. So what kind of a sign will alpha have, Em? Yeah, it's going to be positive. Good, both of you guys. So we have to recognize that if I just put alpha times r here, it's not going to be mathematically sound, right? Because they're going to disagree with each other. Alpha is a positive quantity, and so is r. So when I replace that, I have to take into account that negative sign there. Okay, again, because A is absolutely going to be negative, but because I'm replacing A with a expression that's equivalent to it, I'm replacing it with alpha r, which is equal to the magnitude of A. The magnitude of A, remember that. So the actual A value here is definitely negative because of the fact that it's accelerating downward. So now what we have to do is we have to look at these two equations and combine them. And notice what we're going to do. We're going to combine these two equations, and I'll star them, this one here with this one right here. And what are the unknowns in these two equations? Well, the unknowns are the tension and the alpha value. Those are the unknowns. Everything else in the problem is given. So we have to combine those two equations with each other so that we can get a solution that gives us tension and alpha. And again, tension can be in part C, and alpha can be the answer from part B. So we're kind of doing parts B and C together, and you'll notice that happens a lot, and that was kind of what you had to do on the quiz today. Once you solved for not alpha, but A on the quiz, you could use that A value to then determine the tension. Okay, because it was a system on the quiz today as well. It was a system of equations that needed to be solved there. All right, so let's go through this process. Let's take, well, since we want to find the angular acceleration first, let's go ahead and solve for T1 and replace it in the other equation. So I'm going to solve for T1 at the bottom here. I hate this thing, it's going to slip. There we go. So again, I times alpha divided by R1. Let's take that quantity right there, and let's plug that in right there for T1. What will that yield? That will yield I alpha over R1 equal to, and let's keep in mind that we are really looking at the hanging mass, so this is also R1. Take a look where I just added a 1. That's also R1, because this had to do with the sum of the forces acting in the vertical direction for this mass, which was this guy, which is on this disk, which has a radius of R1 there. We're probably not going to use the R2 again, right? You notice that? Because the second mass is no longer there. So it doesn't make sense that we even have to worry about R2, but because we're calling things R1, let's be consistent. So that goes in for tension, and that's going to be a minus sign next, not an equal. Let's put a minus sign there. Okay, I can't for some reason erase. Let's put a minus sign. Minus M1G equals negative M1 alpha R1. So at this point, all we have to do is solve for alpha. So let's move things over with alpha. So again, what am I doing? I'm taking this expression, adding it over, taking this expression, adding it over, to yield this equation right here. And then I'm going to factor out alpha. And then divide through to get alpha by itself. And then we can plug in a number for that, or the numbers for that. We have M1, we have G, we have I, we have R1, we have everything in the problem. Remember that G is 9.8. Please remember, G is 9.8, or 10, but it's not negative 9.8. How do I recognize that it's not negative 9.8? Here's how I do it. I recognize it because earlier on, I already took into account, right here, that gravity was negative. Because tension is pulling up, gravitational pull is downward, right? And downward is negative. That's where the negative sign comes from. And again, this acceleration is also negative here because it's downward. So that would be the alpha value. I don't have a number for us right now. Let me quickly come up with it. M1, 20 times 9.8. Somebody's sound is on that's loud. Yeah, thank you, whoever had that. Try and mute yourself, guys. I is going to be 45 divided by R1. R1 is 0.5. And then denominator plus M1 times R1. M1 is going to be 20 times R1, which is 0.5. Close my denominator. All divided into 196. Looks like we're going to get 1.96 radians per second squared. Okay, feel free to check my numbers just to make sure I typed it in right, but I did it real quick and it looks right. Yeah. Now, and I use 9.8 for gravity there. So that's going to give us the alpha value. What is the easy way to find the tension now in part C? What's the easy way to find tension in part C now? Very good, Chip. So use this expression right here. So when you solve a system, it's very easy to use substitution because once you get the first one, again, take that and plug it back into the first one and you'll get the other thing there. So let's reuse this equation right here. T1 equals I times alpha all divided by R1. So 1.96 times 45 divided by 0.5. 176.4. Okay. So parts A, B, and C, parts A, B, and C I think are pretty okay. Part D is the part that makes this a little bit trickier. So let me take any questions you might have on parts A, B, or C. Matt, what do you got? Did it? Oh, the 55 limit? Yeah, I know. Okay. All right. So you guys could go if you want. If anyone wants to stay around for D, you're welcome to stay around for D. I was going to post the solution. I had Alex write up that solution that he worked with you earlier, but I think his solution for the first one was not right. So I'm going to wait to post that because I looked at his and I don't have the same answer, and I'm pretty sure he forgot a piece of it. So I'll look into that, and if you guys want to see the solution for number 4, which is the one from the lab experiment, you can take a look at that one online later. If anyone wants to hang around, I'll be around for another 5 minutes to do the rest of part D. If not, guys, have a good rest of the day then. You're welcome. You got it, Spence. Have a good day.